All right. Hello, everyone. My name is Emmanuel, and I'm presenting this paper. The first author is my student, Chunxiong Wang, and this is also a collaboration with VLDB'22 from India. So there's various optimization problems that influence the performance of database management systems. For instance, which indexes we create, how we set system parameters, and for instance, how we partition our data. And all of those decisions have significant impact on the performance that we see when processing data. So traditionally, people have developed specialized tools for solving different problems here, which is, however, problematic because there are dependencies between those different subproblems. For instance, you might be able to set parameters that force the query optimizer to use indexes, but whether that is a good idea or not depends on which indexes you have created. So if you take those different tools and generate locally optimal solutions to those problems and compose them, you are not guaranteed to find a globally optimal solution overall. And this has motivated us to create a system that we call UDO, the Universal Database Optimizer. And you can think of it a little bit like the Swiss Army knife of database tuning tools, because it addresses all of those different subproblems by one unified tool. Now, the way it works is this from the user perspective. So users provide a workload to optimize for and a set of parameters that the system should optimize. And I'm going to use the term parameter in a very broad sense in the following. It includes the system parameters of the database system, but it also includes parameters that represent the decision whether a specific index is created or not, for instance. Also, users specify an optimization metric that could be a latency, it could be transaction throughput, or it could be some combination of multiple of those metrics. Now, the output of UDO after user-specified amount of tuning time is the best configuration that it has found so far. Configuration is essentially the total sum of all of those tuning decisions which assign specific values to all of those parameters. Now, our first challenge that we have here is that it is already difficult to find reliable cost models for all of those different subproblems. And that becomes even harder if we try to take into account dependencies between those different problems. So probably in order to reliably assess the quality of one of those configurations, the only thing that we can do is to actually perform a trial run with the user-specified workload in order to measure performance according to the user-specified metric. And that will tell us something about the quality of the configuration. So what we could do is to use some kind of approach which selects iteratively different configurations to try out, then forwards this to a component that I will call evaluation manager in the following, which takes care of the trial run and measuring the corresponding performance. Now, this was essentially our first version, and when doing that, first the challenge is how do we select the configurations that we want to try out in the next iteration. And one thing that we might want to do is to select the configurations that are somewhat similar to configurations that we have seen in past iterations within the same tuning session and which seem to work quite well. Another thing that we might want to do in order to avoid getting stuck in local optima is to select configurations that are very different from all the configurations that we have seen so far. That is called exploration. And really, there's a tension between those two motivations, which is generally called the exploration-exploitation dilemma. And the most principled way to resolve this dilemma is by a reinforcement learning framework. Now, the general setup of reinforcement learning is the one that you see here. We have one agent which interacts with an environment. And it interacts with the environment by applying so-called actions, and from those actions result reward values. Now, the goal of the agent is to maximize the accumulated reward values, but at least initially, the agent doesn't know the dynamics according to which the environment works. That means the agent first has to find out by a principled version of trial and error how to maximize the reward by specific action sequences. Now, mapping this generic scenario of reinforcement learning to the problem that we have here, the agent, that is, of course, the UDO system, actions are associated with changing parameter values, and the environment is characterized by workload and by system properties. The reward values are representing performance improvements according to the user-specified performance metric, comparing the current configuration against the default settings. So this is what UDO is using in order to figure out which configuration to try in the next iteration and to evaluate it via trial runs. Now, when doing this, it turns out that the system actually takes a long time to find good configurations. And the problem is that each of those iterations that it performs takes quite a while. Now we looked into this in more detail, and the cost per iteration really consists of two components. First of all, there's the actual time for the evaluation, meaning for performing the trial run and measuring the performance. And then there's also the cost for just creating the configuration that you want to evaluate, which might entail, for instance, creating specific index data structures. And as it turned out, in practice, actually the first component of those two is dominant. You have to wait for a significant amount of time until all those indexes and materialized views are created. And looking a little bit closer, it's not all parameters that are problematic. It is a specific subset of those parameters that I will call heavy parameters in the following. And those heavy parameters entail, for instance, parameters related to index creation decisions. It will also entail parameters of the database system, where change of the value requires a server restart, which also takes a little bit of time. So in general, those heavy parameters are parameters where it's very expensive to change the value, and they are primarily responsible for high reconfiguration overheads. So what can we do? Now, the first thing that we did is to change the structure of our optimization problem and go to a nested problem structure. That means, more precisely, that we will optimize separately the settings for heavy parameters and for light parameters. And more specifically, we do this in a way that we keep the settings for the heavy parameters constant, static, for a little bit, while we are trying out different value settings for the light parameters, because that can be done with a very high frequency. And as you can imagine, doing this depending on the ratio at which we revisit heavy parameter settings and light parameter settings can significantly increase the frequency of your iterations, which means that you can converge faster. And in the paper, you also have the proof that even with this change of the problem structure, you're still converging to optimal solutions. Now still, reconfiguration overheads, even with this change, are non-negligible. And when analyzing that in more detail, it turns out that specifically we are paying for cases where we want to evaluate configurations in two consecutive iterations that are very different. Because, for instance, we might have to create a lot of new indexes or materialized views in order to go from the first configuration to the second configuration. So what can we do about that? Now the problem here is that the interaction between the optimizer component and the evaluation manager is pretty restrictive. The reinforcement learning algorithm selects a configuration and then it expects the evaluation manager to evaluate it immediately in order to generate reward values. So instead of that, we make things more flexible and essentially make the interaction between those components asynchronous. So in a reinforcement learning component selects batches of configurations to try it out, and then the evaluation manager has some flexibility in deciding when it wants to take care of evaluating those configurations. And why is that helpful? Well, it is helpful because if the evaluation manager can choose a little bit when to evaluate those configurations, it has enough flexibility often to ensure that configurations evaluated in consecutive iterations are pretty similar, and that reduces reconfiguration overheads. So more precisely, in the evaluation manager, we solved an optimization problem, which we call the reconfiguration problem. And in this problem, we are trying to optimize the order in which we evaluate a certain batch of configurations in order to minimize the reconfiguration time. It turns out that this optimization problem is NP hard, as we show in the paper. And that means that you only have the choice between either using polynomial time algorithms, which might generate suboptimal solutions, or using algorithms with exponential worst case runtime that guarantee to generate optimal solutions. Now in the paper we do both. We have a greedy algorithm and we have one based on integer linear programming, and we also compare the pros and cons of those approaches experimentally. Besides the evaluation manager, however, we also have to change the reinforcement learning algorithm. Now, in a traditional scenario, the reinforcement learning algorithm expects to receive reward values directly in response to actions that it takes. Instead of that, we deliberately introduce a delay between an action is taken and the associated reward becomes available. And in order to handle that well, we have to change the reinforcement learning algorithm and use a specialized version. And this is what we have done. An extended version of this algorithm has been published by the same team at AAAI this year. We call it procrastinated tree search. Now, to show you a little extract from the experiments, in those experiments, we evaluate the system versus various baselines, and we focus on 3 of those sub-problems: index selection, configuration of system parameters, and the selection between multiple semantically equivalent transaction templates. And those are problems that are typically treated separately by existing tools. Now here, for instance, we have results when optimizing MySQL for a TPCH. And on the x-axis, you see the optimization time, whereas on the y-axis, you see the execution time for TPCH queries. And first of all, you see that when comparing UDO with a simplified version of UDO, which does not allow for any delays in evaluating those configurations, actually the performance degrades from the best algorithm to the worst algorithm compared to those baselines. And when comparing this with other reinforcement learning algorithms such as TDPT or SARSA, which don't use those mechanisms in order to reduce reconfiguration time, it also turns out that UDO performs significantly better. Well, the last baselines correspond to combinations of previous optimization tools, which focus only on specific subproblems. And as you see here, combining those solutions for different subproblems does not lead to optimal performance either. Now, this is TPCH. You see similar results when optimizing throughput for TPCC. In the paper, you see experiments with more database management systems, with more metrics, also combined metrics, and you find more in-depth analysis of how those different design decisions of UDO contribute to its performance. All right, so in summary, we have seen UDO, which is the Universal Database Optimizer. It's essentially the Swiss Army knife of automated database building tools. And one of the particularities is that it tries to amortize reconfiguration overhead over multiple iterations, which becomes possible by a reinforcement learning algorithm that is tolerant to delays. You find more details about the algorithm in the AAAI paper, and the code of UDO is available online on GitHub. So thank you for your attention, and now I look forward to your questions.
Thank you, Manuel. Very interesting. We have one question from the audience here.
So the entire idea of ordering reconfigurations is quite intriguing, but did you also consider a deeper integration into the actual system? So for read-only workloads, I could imagine that by modifying the catalog, what the optimizer actually sees is that you can integrate it in a way to create an index just once, and then for different configurations, just keep that index around, make it invisible to the optimizer to not being picked up in order to avoid absolute redundancies, potentially even improving upon the ordering where it might not be possible to avoid reconstructing an index at all.
Okay, those are very good points. So, I mean, one of the design goals was essentially to keep the system as generic as possible in order to apply it with many different database management systems and on many different types of workloads. I think you could do that to some degree for certain systems. One thing to pay attention to is that you may not have enough space to create all candidates for indexes and materialized views. So even if the system supports that, you might still have some constraints about like having to reconfigure every once in a while. So I think that you can, I think it's a great question. I agree, you can probably apply optimization specialized to certain systems and scenarios, but you probably still want to have a mechanism like that in order to cover the cases where you still have to reconfigure.
Excellent, makes perfect sense.
Thank you.
Thanks for the talk, really nice work. So also, I think it's pretty related to the question before. So my question was like, one alternative could also be to just allow the agent to select exactly one. So one action could also be just a single thing, right? Change one index, change one parameter, right? Do you think that would make sense, or do you think that would probably not work as good as the delayed evaluation approach? Because then, like by nature, you don't have as many changes per step, right?
That is true, but I mean, nevertheless, you would have one change per step. I mean, the nice thing about the delayed version is that you essentially give the control about what to evaluate in which order to the system. So in this case, for instance, you might group together many configurations which don't require any expensive changes in the best case. We thought about a couple of different variants. One thing that we also considered was to essentially give the reinforcement learning algorithm some information as part of the reward function in order to try to make it explore the space of alternatives cheaply. But we did not use that in the end because that would introduce some conflicting objectives, which is you might not go for the optimal configuration because it looks scary about all the things that you have to change from the current configuration in order to get there. So here what we are doing, we are essentially separating the concerns. The reinforcement learning algorithm only thinks about finding those optimal configurations, whereas the evaluation manager only thinks about how can I keep reconfiguration overheads low.
Okay, thank you.
Sure. Great questions.
I sort of have a follow-up question, a quick one. Can you comment on search space and that problem? What are the possible configurations, or the number of possible configurations for the heavy parameters and the light parameters? How many light parameters are there?
Okay, very good. So in total for those different systems, we use something like about 100 parameters. And I'm unsure how many of them, so I think a little bit less than half of them were heavy parameters.
Wow.
The most significant heavy parameters are those index candidates in particular. For the light parameters, you have in particular parameters related to changing which transaction template you want to use and changing the settings for certain system parameters which don't require a restart of the database server. So it is definitely a large search space. So one thing that we're doing, we are enabling essentially a limited number of changes compared to the default configuration, which is essentially based on the assumption that typically in order to optimize the configuration, there are a few key parameters that you want to change, but you may not know in advance which are those key parameters and even like what type of parameter it is. Will you get significant performance improvements by creating one new index, perhaps for an analytical workload in particular, or also for other workloads, or will you get better improvements by changing, for instance, the shared buffers settings of the system? And that depends on the scenario. So this is why the system wants to explore all of those different parameters in one holistic approach. Otherwise, even if you have some learning-based approach, we have to decide how much time to dedicate to different types of parameters and optimization. Here the system figures it out automatically.
Perfect. Thank you so much, Emmanuel. It's your stain. Fifth and final paper are also from Cornell University, Codex DB, synthesizing code for query processing from natural language instructions using GPT-3 colleagues. Are you working on that? Good. I guess
There was a flicker in the screen as press.
Hi. While they are preparing for the TV, I would like to ask one more quick question about the last paper.
It's a quick one, 1 minute.
Yeah, just 1 minute. So you are taking a reinforcement learning to take the reconfiguration or something. So I believe it's instance optimized thing. So I wonder what's the input of the reinforcement learning agent. So I believe you have input the current configurations into that agent. So do you also include some other information like the data set or like the resources? Could you bring more details about that?
So you're asking about the input that we're providing to the agent?
Yes, it's basically I'm asking about the states that you like take into
Right.
account.
So the states are essentially characterized by settings to those parameters. We express everything by like settings for those parameters, which could represent whether one index is created or whether one system parameter is set to a certain value. And those states are entirely defined by the settings to those parameters. So essentially you're moving between different states which represent different configurations in the end.
Alright, so it's nothing to do with the actual data set that you are like
So the way you specialize, yes, so I mean the state does not contain any information about the data set. How you get information about the specifics is essentially by the reward function. So over time the agent sees which combinations of settings result in optimal rewards.
So for each data set instance, you need to retrain about the policy to.
Exactly.
Alright.
So I mean this is basically everything happens with one tuning session.